Okay, we are back again to this equation, right. Now, to solve for g desired, we must solve for delta x using equation 36, right. Earlier 36 I have shown. Then calculate x new, the new values of all x, right, is equal to x plus delta x, and reapply equation 36 until either delta x get very small or g x come close to g desired, right. Now, let us return to the state estimation problem as given in equation 30. So, earlier we have seen that your minimize your j x I is equal to 1 to n m, that is number of measurement, then in bracket z I minus f I x whole square divided by sigma I square. I told you once again that why you have divided it by sigma I square, it is a small question to you, right. So, you will apply, you will answer it in forum. First what we have to do is, we have to first find out the gradient of j x. So, gradient of j x, it can be written as delta j x delta x 1, delta j x delta x 2 and so on. You have ns number of state variables, right. So, this way you have to find the gradient. Now, and this is the function j x. So, you have to take derivative with respect to x 1, x 2, x 3, right, all partial derivatives you have to take. Now, if you do so, then gradient of j x, it can be written as that minus 2 will come because of your this thing, because square is here, right. If you do so, then it will be minus 2 into delta f 1 upon delta x 1, delta f 2 upon delta x 1, delta f 3 upon delta x 1 and so on, right. You have if you look into that, you have I is equal to 1 to n m. So, n m number of measurement. So, it will go up to n m. So, then delta f 1 upon delta x 2, delta f 2 upon delta x 2, delta f 3 upon delta x 2 and so on, right. So, actually it is continuing, it is also continuing, it will also continuing, understandable. Then this term automatically will come 1 upon sigma diagonal matrix 1 upon sigma 1 square, 1 upon sigma 2 square, it will continue, all other elements are 0, that is why these are shown as 0, right, into z 1 minus f 1 x, z 2 minus f 2 x, and it will continue because you have n m number of your measurements, right. Now, if we put that f I x function in a vector form f x and calculate the Jacobian of f x, we would obtain. Now, if we write delta f x upon delta x in general, right. So, it is actually it will like if you do it. So, it will be delta f 1 upon delta x 1, delta f 1 upon delta x 2, delta f 1 upon delta x 3 and so on. Similarly, delta f 2 upon delta x 1, delta f 2 upon delta x 2, delta f 3 upon delta f 2 upon delta x 3 and so on. So, it is basically Jacobian matrix, it is basically Jacobian matrix. If you look into this matrix and if you look into this matrix, you will find it is transpose of another one, right. Therefore, we call this matrix H, that means this matrix, this Jacobian matrix, this one we are calling is as a matrix H, right. So, basically this is a Jacobian matrix, Jacobian of f x, right. That means this H can be written as delta f 1 delta x 1, delta f 1 delta x 2, delta f 1 delta x 3 and so on up to n m number of your what we call measurement you have, right. Similarly, delta f 2 upon delta x 1, delta f 2 upon delta x 2, delta f 2 upon delta x 3 and so on, right. Therefore, it transpose is, if you take the transpose of this matrix, it H transpose, it will be delta f 1 upon delta x 1, delta f 2 upon delta x 1, delta f 3 upon delta x 1 and so on. So, delta f 1 upon delta x 2, delta f 2 upon delta x 2 and delta f 3 upon delta x 2 and so on, right. That means, this equation, this actually this will be H transpose, right. And then that is your, then this one that your R is equal to sigma 1 square, sigma 2 square. Initially at the beginning of the state estimation R, somehow I overlooked that one. I mentioned that it is R inverse, it is not R inverse, it is R, right, because it is 1 upon sigma 1 square, right. So, when you take R inverse, at that time it is basically R matrix, right. So, we are defining like this. So, everything is actually everything is okay. So, now equation 38 now can be written as that it is, if we take this one is R, that is 1 upon sigma 1 square, 1 upon sigma 2 square will come because it is a diagonal matrix, that is why this R inverse, right. So, equation 38 can be written as the gradient of j x actually is equal to minus 2 into, then I told you it will be H transpose, then R inverse into z 1 minus f 1 x, z 2 minus f 2 x and so on, right. That means, this equation that means this equation minus 2 H transpose then R inverse, because R is equal to sigma 1 square sigma 2 square like this, and these are all 1 upon other elements are 0, that is why R inverse, and this is Z 1 minus F 1 x Z 2 minus F 2 x, right. So, that is this is the equation 43, right. Now, to make this gradient 0, right, we will apply Newton's method as given in equation 37, right. So, in equation 37 actually this is actually assume that your g x is equal to gradient of j x, right. Therefore, g, that means g dash x will be del x of gradient of j x, because you have to solve it iteratively, right. So, in that case you have to first first to assume g x is equal to the gradient of j x, then g dash x will be del x of gradient of j x. So, you have to force the gradient to 0 iteratively. So, we know that formula, that delta x is equal to, just now we have done it in equation 37, right. It is actually g dash x inverse into minus g x, right. So, g dash x inverse minus. So, this is your g x. So, that is why it is minus gradient of j x, and this is your g dash x, that is your del x of gradients of j, derivative of this one. So, this is actually delta x. So, this is equation 44. I hope this is understandable to you, right. So, now the Jacobian of that gradient j x is calculated by treating H as a constant matrix. Now, I assume H is a constant matrix, then what we will do, that is del x of gradient of j x we have to compute. That means this is my your gradient of j x. We are assuming H is a constant matrix, R of course is a constant matrix, H is a constant matrix, then you have to take the derivative with respect to x of this gradient, right. So, if you do so, that equation 43, if you do so, then del x of gradient j x is equal to del x of minus 2 H transpose R inverse into the Z 1 minus F 1 x, Z 2 minus F 2 x, and so on, right. So, if you take this thing, then it will become actually minus 2 H transpose R inverse, and if you take the derivative of, again it will come your, in general it will come del f upon your what you call del f upon del x in general. So, basically it will be nothing but your Jacobian matrix, because here we have shown that if you take del f x upon del x, it is nothing but your Jacobian matrix, that is your H, right. Here it is H. So, that is equation 39. So, that means if you take with respect to this one also, so basically it is minus sign is there, so minus will be there, and in general del f upon del x is nothing but the H, the Jacobian matrix, right. That means the gradient of your derivative of this gradient is nothing but 2 H transpose R inverse H, right. This is equation 45. So, this is after doing this you have got the gradient, right. So, assuming that H and your all H matrix is a constant one. So, next is, then we know that delta x is equal to your, what we have seen, delta x is equal to g dash x inverse, right. G dash x is nothing but the gradient's derivative. So, this is our g dash x, that is del x of gradient of j x. So, that is H transpose R inverse H inverse, right, and was 2 was there. So, because of this 2 we have made it 2 inverse, that is half. So, it is half, right, because here, so here it was 2 was there. So, when you take inverse of this one, inverse of this one, as you are taking inverse, so because of 2 it will be half, and then H transpose R inverse H inverse, right. So, that is what we are writing there, that is what we have written here, right. Half H transpose R inverse H whole inverse into the 2 H transpose R inverse Z 1 minus F x 1, Z 2 minus F 2 x, F 2 x, and so on, right. So, 2 will be cancelled, this is 2 and this is 2 will be cancelled. So, ultimately it will become delta x is equal to H transpose R inverse H whole inverse H transpose R inverse Z 1 minus F 1 x, Z 2 minus F 2 x. This is equation 46, right. So, equation 46 is obviously close parallel to equation 23, because if you look equation 23 you will find very close to that, right. to solve the AC state estimation problem, you apply equation 46 iteratively as shown in figure 10, that in a flow chart is given, right. So, note that this is similar to the iterative process used in the Newton's power flow method. It is basically Newton's method, that your what you call that your iterative method, right. Now, if we come back to this, your what to just let me reduce the size. So, if we come back to this, that first you have to start, then read measurement, that means all z measured values, all the measurement data you read, then pick starting value for x is equal to x naught, right. Superscript is given, x is equal to x naught. Then you solve for your what you call z I minus f I x for I is equal to 1 to up to n m number of your measurement, right. So, once you made it, then calculate H matrix as function of x, right. So, that also you have the H matrix, I told you, that is a Jacobian matrix of f actually, right, and with the initial values you have to calculate H also, right. If it is not this thing, if it is not function of x, then directly you will get it, right. So, calculate now H transpose R inverse H matrix, right. So, that you can calculate. Now, calculate H transpose R inverse H inverse. Now, you have to calculate this one, right, step by step. Then you solve for delta x using equation 46, that this equation, that is your this using this equation you solve for delta, that is delta x 1, delta x 2, like this. It is in general is a what you call is a vector, right. So, once you have done this, right, then calculate maximum of delta x I. I mean you have so many your what you call, you are getting I am just let me increase the size, right, just hold on. So, let me increase the size, then I will tell you this one. So, suppose what you are doing is, suppose you have so many variables, that delta x I, right, is equal to delta x 1, delta x 2, like this, you have n-s number of state variable, right. So, every time you are trying to find out the mismatch, right, then you are taking absolute, that what you take, that you take absolute of your delta x 1, I am putting in my way, then absolute of delta x 2, all you are taking for n number of state variables, right, out of which what you do, you find the max of that. That means, here I am making like this, but then for your understanding, suppose delta x max is equal to your max of, right, your delta x 1, then delta x 2, like this, right. You find out maximum, take all the your what you call delta x values, and take out of which the maximum one, absolute, of course, the absolute value will take, right. And if that max value, if that delta x, that is max, delta x I is nothing but the your delta x max. If that max value is your less than epsilon, you specified epsilon, for example, say 10 to the power minus 4, you specified epsilon. If it is less than epsilon, your solution has converged, right. Otherwise, that means if it is less than epsilon, yes, then your what you call, then your it is solution has converged, that is your yes, right, that is done. If it is not, then you update x is equal to your x plus delta x, that means x 1 is equal to, in general x 1, I mean in general iterative method, when you write, that is in general it will be x I k plus 1 is equal to x I k, right, plus delta x I k, that is in general. So, that is why I mean in the flow chart form we have written x is equal to, x is a vector actually, right, so many state variables are there. So, x is equal to x plus delta x. So, update, and after updating that you will come back to this thing again, you start, right, you got the new value of x, your what you call x, then again solve for this one and repeat this process till the solution has converged, right. So, this is actually AC, but only thing is that in AC network, right, we cannot solve problem in the classroom without computer. So, whatever little bit, whatever you given it from the steady state point of view and theory point of view, right. So, otherwise it is not possible. So, next is your what you call that your state estimation by orthogonal decomposition. So, in this case that what happen, why you will go for orthogonal decomposition. So, basically in this method we will use one thing, any orthogonal decomposition, you can see any control system book or any article also, any control system book or any optimization thing, that orthogonal decomposition you will get. And here in this course it is not possible to explain in detail that Given's rotation method will be used, right. So, directly I will tell you, right, and if you have any problem, then you put the question in the forum, we will see that, but Given's rotational method will be used. So, those Given's rotational method cannot be explained here, but directly I will write, assuming that you will study of your own only this part, only this small part, right. So, now state estimation by orthogonal decomposition, that why we will go for orthogonal decomposition, definitely there must be some reason for that, right. So, one problem with the standard least squares method presented earlier is the numerical difficulties encountered with some special state estimation problems, right. Sometimes that matrix may become singular or something like that. So, you may not get any result, right. You have to overcome that. One of these comes about your when wish to give a state estimation solution to match its measurement almost exactly, right. So, this is the case when we have a circuit which are shown in figure 11, right. So, this is actually W12 measurement is 32 megawatt say, right, and this is your load, here your load is there or generation whatever you will take, it does not matter, that it is meter 1. So, its reading is 0, it is 0, right, and another meter is there, that is your W32, it is 72 megawatt, all are megawatt, right, and this is your what you call that your per load is going that 100 megawatt, and here it is 100 megawatt is entering, because if you just go for power summation thing, then you will get this result, right. So, these are meter. So, meter means same thing, it is actually M12 is nothing but W12, right, it is M is nothing but your W32, right, and here it is M1. So, it is basically W1. So, same thing, right. By when I writing meter, so I put meter here W and M, that is why I made it here W, here it is W and here it is W, such that there should not be any confusion, right. So, 0 injection system example. So, here injection should be 0, right, because load is 0. So, no power injection. So, these are the things. Suppose this is meter reading and these are the thing. Now, some data we have taken and given this thing, right. So, now all of the actual flows and injections are shown in figure 11. So, this is meter reading and based on that some line flows and other things are given, some data are given, these are the given data, right. Now, in this example, the measurement power at bus 1 will be assumed to be 0 megawatt, that is here at bus 1 that measurement power will be 0 megawatt, right. Suppose if the value of 0 is dictated by the fact that the bus has no load or generation attached to it, then you know this value of 0 megawatt with certainty, and the concept of an error in this measured value is meaningless, right. Now, nonetheless, we proceed by setting up the standard state estimator, right, equations and specifying the value of the measurement sigma for M1. Suppose for M1 that sigma M1, that is a standard deviation, is 10 to the power minus 2 for meter 1, which was connected near bus 1, right. This result in the following solution when using the state estimator equation 33. Suppose if we do so, suppose power flow estimate on line, suppose this data is given 1 to 2 30.76 megawatt using the your same data. Now, power flow estimate on line 3 to 72.52 megawatt and injection estimate on bus 1 is 0.82 megawatt. That means, this is not 0, because although we expect it should be 0, but it is showing some 0.82 megawatt, and in a power system you have a huge many numbers of measurement things are there. So, gross error will be quite large, right. So, the estimator has not forced the bus injection to be exactly 0, instead it reads 0.82 megawatt. This may not seem like such a big error, right. However, if there are many such buses, say 100 buses in a network, right, and they all have errors of this magnitude, then the estimator will have a large amount of load allocated to the buses that are known to be 0, right. So, at first the solution to this dilemma may seem to be simply forcing the sigma value to a very small number for the 0 injection buses and rerun the estimator. The problem with this is as follows, right. Suppose we had changed the 0 injection sigma for that is sigma M1 is 10 to the power minus 10. That means, the meter is actually very accurate, 10 to the power minus 10 sigma means it is almost 0 error, right. Suppose you have made it, hopefully this would force the estimator to make the 0 injection so dominant that it would result in the your correct 0 value coming out of the estimator calculator, right. In this case, the H transpose R inverse H matrix used in the standard least square method would look like this for the sample system. Sorry. So, H was given, the same H was taken previously. So, in this case of your what you call your R, only your meter 1, it is not all minus 20 this thing, right. Only for sigma 1, that is sigma m 1, we have taken 10 to the power minus 10. So, square will be 10 to the power your minus 20, right. So, this R is given 10 to the power your, this is actually other things remain same previously. So, it will be 10 to the power minus 4, 10 to the power, this is actually 10 to the power minus 20, right. So, if we do so, then H transpose R inverse H, actually it will be something like this, 56.25 into 10 to the power 20 minus 37.5 into 10 to the power 20 minus 37.5 into 10 to the power 20 and 25 into 10 to the power 20. These values are very large, right. Unfortunately, this matrix is very nearly singular, right. Singular means its inverse may not exist, because you have to ultimately you have to calculate this inverse, right. So, in this case what will happen, the reason is that the terms in the matrix are dominated by these terms, which are multiplied by the 10 to the power 20 terms, right, from the inverse of the R matrix, and the other terms are so small by comparison that they are lost from the computer. That means, unless one is using an extraordinarily long word length or extra double precision, right. So, when the above is presented to a standard matrix inversion or run into a Gaussian elimination solution routine, right, an error message will result and garbage comes out of the estimator, because you will not get anything, because matrix becoming singular. So, the solution to this dilemma is to use another algorithm of the least square solution, and this algorithm is called the orthogonal decomposition algorithm and works as follows, right. So, that is why we follow orthogonal decomposition, such that you will get a reasonable good solution. So, the orthogonal decomposition algorithm, this algorithm actually goes under several different names in text on nonlinear on linear algebra, right. It is often called QR algorithm or the Gram-Schmidt decomposition technique, right, because but here we are not using this QR algorithm or this thing, because we are using R matrix something, right. So, we will name this as a QU rather than QR algorithm, right. The idea is to take the state estimators, your what you call least square equation, that is equation 23 we have seen, and eliminate the R inverse matrix as follows. So, we have to eliminate R inverse, because this actually creates problem. That is why you go for orthogonal decomposition. So, R inverse you can write R to the power, it is actually earlier I wrote that it actually your what you call in bracket R to mention R matrix, the same thing, this R actually this R, this is same thing, just to write in bracket again and again, I did not put it, right, I did not write it. So, it is R matrix actually, right. So, this R inverse, it can be written as R to the power minus half into R to the power minus half, right. That means your where R to the power minus half will be actually, earlier it was R to the power your what you call earlier R to inverse, it was 1 upon sigma m 1 square, 1 upon sigma m 2 square, 1 upon sigma m 3 square, like this. So, in this only you have taken that your 3 measurement case, right. So, therefore, R to the power minus half will be 1 upon sigma m 1, 1 upon sigma m 2, 1 upon sigma m 3, like this. This is equation 48, right. Therefore, this equation H transpose R inverse H inverse H whole inverse is equal to, we can write H transpose R to the power minus half into R to the power minus half into H to the power minus 1, right. That can be written as H dash transpose H dash, because this one if you assume that this is my H dash, this is my H dash is equal to R to the power minus half, then your H, right. This you have, then H dash transpose will become H transpose, right. Then your what you call that your R to the power minus half, because it is a diagonal matrix. So, no question of putting transpose, right. So, that is why this one we can write that H dash transpose into H dash, this is equation 49, right. So, with H dash is equal to, just hold on, with H dash is equal to R to the power your minus half into H, right, that is equation 50. Finally, equation 23 will become that x estimated is equal to H dash transpose H dash to the power inverse into H dash transpose into J dash measure. This is equation 51, right. Now, let us assume what we have done is that Z dash measured is equal to r to the power minus half into Z measure, right. So, this is equation 52. So, just to assuming this, right. So, that is why it is Z dash measured. Now, the idea of the orthogonal decomposition algorithm is to find a matrix Q such that H transpose is equal to Q U, right. This is equation 53. The matrix Q has a special properties. It is called an orthogonal matrix. So, that Q transpose Q will be identity matrix I, right. That means, Q transpose will be is equal to basically Q inverse, right. So, this is Q transpose Q is equal to say I, where I is the identity matrix, which is to say that the transpose of a Q is its inverse, right. The matrix U is now an upper triangular in structure. Although, since the H matrix may not be square, U will not be square either, right. Therefore, we can write H dash is equal to H dash 1 1, H dash 1 2, H dash 2 1, H dash 2 2, H dash 3 1, H dash 3 2 is equal to Q U is equal to Q is a 3 into 3 matrix. It will be Q 1 1, Q 1 2, Q 1 3, Q 2 1, Q 2 2, Q 2 3, Q 3 1, Q 3 2, Q 3 3, and U is a upper triangular. So, U 1 1, U 1 2, it is 0, U 2 2, and it is 0 0, right. Now, if we substitute Q U for H dash in equation 51, in equation 51 you just substitute that your this thing, right, you substitute here. If you substitute, then you will get x estimated will be U transpose Q U whole inverse, then U transpose Q transpose Z, right, Z dash. This is equation 56, where Z dash is equal to Z dash measured, right. Therefore, x estimated will be U transpose U inverse, because Q transpose Q is equal to identity matrix I, right, because this Q transpose Q is equal to identity matrix I, right. Therefore, your this x estimated will be U transpose U inverse into U transpose Z cap, right. So, Z, that is your Z cap is equal to Q transpose your what you call Z dash, that is Q transpose Z dash is equal to Z cap, and Q transpose Q is equal to I. So, this is actually I, right. So, our objective was to eliminate that R inverse, that is R matrix, from that mathematical equation, right. So, then by rearranging you will get U transpose U x estimated is equal to U transpose Z cap. This is equation 59, right, and we can eliminate U transpose from both sides. So, that we are left with. So, both side U transpose you can eliminate. So, you are left with U x estimated is equal to Z cap. Look how simple it has come now, right. The expression finally has become in a simple form by orthogonal decomposition, right, or U is equal to U 1 1, U 1 2, it is upper triangular. So, 0 U 2 2, 0 0, x 1 estimated, x 2 estimated, this is Z 1 cap, Z 2 cap, and Z 3 cap. So, if you solve this one, then x 2 your estimated is equal to Z 2 cap upon U 2 2, this is equation 62, and x 1 estimated is equal to 1 upon U 1 1, Z 1 cap minus U 1 2 x 2 estimated, right. For the Gibbons rotation method, we start out to define the step necessary to solve, right. So, this Gibbons rotation method actually little bit we will see, not much, little bit we will see, and then your what you call then we will try to see few examples at the end, right. So, we will make few examples for you, and throughout the course it actually its course is mostly your mathematical oriented, and mathematics are there. So, and all the problems are not small problem, but we will see how things can be done, right, and all this analysis we have tried to see it. So, thank you very much, we will be